Okay, kiddos, here's a video lesson explaining the electric field. These are the notes that I had intended to write up on the board. So, what we have here is positive charge, and there are lines pointing away from it. So when we talk about the electric field, it's very similar to the gravitational field. And when you're on the surface of Earth, so not drawn to scale, but when you're on the surface of Earth, you feel a force downward, and so that's the pull of gravity, obviously. It turns out that mass attracts mass. And so to explain the fact that something, so here's a bird. So to explain the fact that something away from something else experiences a force, we talk about this thing called a field. And so we say that surrounding some big mass like the Earth, there is a field, meaning an object with mass in that location will experience some force. We do the same with electric charges. So a positive charge has an electric field around it because a positive charge here will experience a force in this direction. A positive charge here will experience a force in this direction. So we sort of define a field as a property of space that relates to the force something would experience. Let's see what I have on the next. Alright, so here's this concept of action at a distance. We have a whole lot of experience in touching stuff and having it move. So in order to exert a force on this block, we would have to touch it and move it. And so in science fiction movies, you see people that have that ESP, extrasensory perception, or telekinesis or whatever, and they can bend spoons with their mind. But yet we don't really see that in everyday life. But what we do see is we see mass acting on mass from some distance away. And so charges can do the same. An electric charge can exert a force on another electric charge from some distance away without touching it. We refer to that as action at a distance. The electric field is defined as the force per charge. And we have these little arrows above the electric field and the F for force because these are vector quantities. So you remember a vector quantity is something that has magnitude and direction. I'm yelling because the heater is going in the background, and I hope that sound is not too distracting. So these are vector quantities, and in physics books, sometimes you'll see these vector quantities as bold letters. To keep things simple, I tend to just not write that and assume that you know that the force that something experiences has some direction associated with it. Okay. So electric field lines point in the direction that a positive test charge would feel a force. I'll say that again. Electric field lines point in the direction that a positive test charge would experience a force. So if we consider this positive test charge, meaning you think, okay, I'm going to just take a little positive charge and put it in this location, these charges remain in place, what kind of force would this experience? So this guy right here would be pushed away by that positive charge, and it would be pulled by this negative charge. And the resulting forces, because they're about the same distance away, the result of those two forces would be something like this. So if I can't erase, if I get out of there, oh, I see. I'm recording, so this is going to be way more challenging. So if we erase, that this guy, and just know that, okay, the force was to the side at that point. what we can do is we can draw these lines that sort of indicate the direction that a charge would experience a force. So do you see how right here the force is horizontal, and we know it would be going like this. So we could draw a little arrow. If it were straight down the middle, it would be like that, and so the field lines tend to do this. So again, these indicate the direction that a positive charge would experience a force. So if we were to take a positive charge and put it right here, yes, it's being pushed by this, but it's being pulled by this, so it would kind of take this path and move around and eventually hit this guy. Same as that path or this path or this path. So we call those electric field lines. Away from positive towards negative. And then there's something else that, that we should know, and that is that the distance between, so you see how these are pretty close together? The distance between the field lines indicates the strength of the force. So a positive test charge here would experience a greater force than one out here. Notice how these field lines are farther apart. So again, the distance between the field lines is an indication of the strength of the electric field force at that point. This is just an image and these are actually magnetic field lines where we have the north pole of a magnet and the south pole of a magnet. And after we learn about electricity, we'll learn about magnetism. But notice how they're basically doing that same thing, where we have this, and so it turns out that magnetic field and electric field really behave very similarly. Okay. And we'll be able to see this in class. Cool. So, when you're solving questions, this is what you'll be using. We know that the electric field is defined as the force per charge. Using this right here, this is called Coulomb's law. We know that. F equals kqq over r squared. So we basically took this. So this is the force between two different charges some distance away. K, 9 times 10 to the 9th, Coulomb's constant. We took that, we substituted it into force per charge. So basically, the Q's cancel. And we're left with something like this. So the electric field strength caused by some charge can be described by this equation, where K is 9 times 10 to the 9th, and R is the distance from the charge, and this is the charge. We would measure charge in coulombs, measure the distance in meters, and well, K has units so that the electric field ends up being units of force per charge, so newtons per coulomb. Newtons per coulomb, units for electric field strength. Oh, we just talked about that. Let's keep recording. Uh-oh. And lastly, so here's a conductor. So did we talk about conductors and insulators? Let's see.